onto the electromagnetic waves chapter. So which best describes the difference between radio and X-rays? So radio waves and X-rays are two different types of electromagnetic radiation. They have different wavelengths. So going into that, that's sort of what I'm looking for here. So X-rays are radiation, whereas radio waves are electromagnetic waves. Both are radiation and both are electromagnetic waves. Those are sort of different words for the same thing. We tend to think of X-rays as being things that can harm us, and in common language we use the word radiation there. But really radiation is any electromagnetic wave. It just happens that X-rays have a high enough frequency that individual photons can actually rip electrons off of cells in your body, and that can cause cell damage, which is why X-rays are harmful. But both of them are both electromagnetic waves and radiation. So both can be thought of electromagnetic waves. That sounds good. They only differ in wavelength and frequency, and that is going to be our answer. They travel at the same speed, so they will have both different wavelengths and different frequencies. X-rays are pure energy, and radio waves are made of field and not energy. That's just incorrect. Radio waves come from electric currents in an antenna. X-rays are not related to electric charge. So kind of related, both C and D are trying to get at the idea that somehow there is something inherently different between these two things. Both of these things being electromagnetic waves are waves that travel in space with an oscillating magnetic field and an oscillating electric field, and the speed where all three of those three things are perpendicular to each other. So certainly you could transmit X-rays with an antenna if you wanted to. It's just not something that we do because X-rays are harmful. So that one's also not true. X-rays are made up of particles called photons, whereas radio waves are oscillations in space. It tends to be true that we notice photon nature of X-rays more because individual photons of X-ray light have more energy per photon than radio waves. But both are made up of photons, and they are both oscillations in space. So that one's not true either. So B is the right answer. The next one, the next two are really just the same problem, 4 different times. So we're calculating the wavelength of a 60 hertz electromagnetic wave, a 93.3 megahertz FM wave, a beam of visible red light with that frequency, and then an FM radio station at 100.1 megahertz. So all of these are exactly the same question over and over and over again. For all of them, you're going to use the relationship that the speed of light is wavelength times frequency. I think I've probably written that equation down like 20 times already on this review sheet. So it's definitely a good one to commit to memory. And since we are talking about things traveling in air, we'll have that the speed of the wave is the speed of light. So it's 3 times 10 to the 8th meters per second. That constant is written on your equation sheet as well. So I'll do one of these out, and then I'm just going to write the answer behind that. So a 60 hertz wave, we want the wavelength. So the wavelength is going to be C over F is 3 times 10 to the 8th over 60 hertz. Go plug that in, and I get, what's that, a 5 with 6 zeros in it, so 5 million meters, so 5 times 10 to the 6th meters. I'll write that to 1 sig fig because of that. For the next one, it's going to be 3 10 to the 8th divided by 93.3 times 10 to the 6th. And that's 3.2 meters, 3.22 meters, I guess, to keep it to the right number of sig figs. Next one is 3 10 to the 8th divided by that frequency, 4.74 10 to the 14th. and I get 6.33 times 10 to the negative 7th meters. You could write that. That's perfectly acceptable. Light waves, or visible light waves, we usually write in nanometers, so that'd be 633 nanometers. But either one is fine and correct. And now we have an FM station, 100.1 megahertz. This should really just be part D, or kind of get rid of it because it's the same as the previous question. So now I have 3 times 10 to the 8th divided by 100.1 times 10 to the 6th. And that is 2.997 meters. There you go. Check these. Let me just make sure on the that's right. So it looks like on my equation sheet for B, I wrote 6.33, but we just calculated it to be 3.22. So I must have been reading off a wrong line in my calculator when I wrote that down. So I'll have to update that on the solutions sheet. But that looks like the right answer to me. And just to finish this off, because we are almost done with electromagnetic radiation, which of the following types of electromagnetic radiation travels the fastest? The answer here is they all travel at the same speed, right? C is lambda frequency. That's always going to be the same. These two things will vary to make that be equal. Electrons vibrating up and down 1,000 times per second. What frequency, or sorry, what will be true about that wave? This is the definition of frequency. How quickly does it go up and down? If it goes up and down 1,000 times every second, it's a wave that has a frequency of 1,000 hertz. All of these other things are not true. You could figure out its speed. That's 3 times 10 to the 8th meters per second. You can't figure out its amplitude from that information, so you couldn't even do that. You could use the fact that you know its speed and its frequency to figure out the wavelength, and it would most definitely not be 1,000 meters. And the last question in chapter 22 is, how long does it take light to reach the sun? So this is the definition of velocity. Velocity is distance over time. So we knew that that is 3 times 10 to the 8th meters per second, and there's the distance, and we're just going to solve for time. So the time is the 1.5 times 10. And the only tricky part about that is that I gave you this in kilometers, so you need to increase that number by 3 there to get that to meters. So it's traveling 1.5 times 10 to the 11th meters, and 3 times 10 to the 8th meters per second. So 1.5, 10 to the 11th meters divided by 3, 10 to the 8th, and that gets us at 500 seconds. That's about 8 minutes. So when you see the sunrise, it actually happened 8 minutes ago.